Hello, everyone. Thank you for joining us for our next seminar, despite the change in day and the change in the Zoom link. Uh, this afternoon, I'm pleased to introduce to you Cale Rankin, who's currently a postdoc at Monash University. Cale's going to be talking to us about the so-called monopolists problem, optimization over spaces of convex functions, and free boundary problems. Thank you, Cale.
Awesome. Thanks for the invitation, Tim. I looked back and it's been about 3 years to the day since I last spoke in one of the Oz geometric analysis seminars, so I'm probably overdue to talk about some new work. So today I'm talking about the monopolists problem. I know that's a problem not many people have heard of, so we're going to spend a fair bit of time introducing it. Before I do, let me mention this is joint work with Robert McCann at Toronto and Kelvin Zhang, who's now at Fudan in China, Shanghai. We're talking about the contents of two papers, both on the archive. One just recently appeared in Advances in Mathematics. So I've called this talk, it's got the subtitle Optimization over the Space of Convex Functions and a New Free Boundary Problem. And that's already hinting at some of the key things in today's talk. We're going to be talking about a free boundary problem, which is not so well known. And we're going to be talking about optimization over the space of convex functions. So a bit more of an outline. We're going to start talking about the monopolist problem. We're going to talk about what exactly it is, why it's an interesting thing to study, and why it's a non-trivial thing to study. Then the talk's going to be split into two families of results. One is results for arbitrary domains, first in n dimensions, then specializing to 2 dimensions. And then the second part of the talk, we're going to be talking about a family of solutions to this problem, the monopolist problem, on the square. So basically looking at some very explicit examples and trying to gain some really precise understanding of how solutions to this problem behave. So first section of the talk, intro to the monopolists problem. What I really want to convince you of is that a plausible or reasonable model, which does initially arise in economics, actually gives rise to what is a very interesting problem in nonlinear optimization and the calculus of variations. I'm going to explain that studying this model requires ideas from Monge-Ampere equations, from optimal transport, and from free boundary problems. Now I'm going to go ahead and hit you with the model right from the start. It's minimize the integral of a half du minus x squared plus u over the space of convex non-negative functions. So for anyone with a bit of background in PDEs or calculus of variations, that first line, minimize a half du minus x squared plus u, looks very simple. Looks like something you wouldn't give a talk about in 2025 because it's a pretty trivial problem in the calculus of variations. Where all the difficulty is going to come from today is the fact that we're minimizing over the space of convex functions. So it's the constraints that make this thing difficult, not the functional we're minimizing. And to understand where exactly those constraints come from, you've got to understand the derivation of this model. So I'm going to give you the economic derivation, and then we're going to sort of switch back to just treating the mathematical properties of the model written there. So it's called the monopolist problem. A monopolist is a person who wants to sell products, but isn't competing with any other sellers. The economic setup is as follows. This monopolist, they've got a space of products to be sold. Here, a product is a point in Rn, and the space of products is a subset of Rn. What does that mean for a product to be a point in Rn? Well, if, for example, our monopolist was selling cars, a car could be parametrized by 3 parameters. 1 is how fast it goes, 2 is how fuel efficient it is, and 3 is how luxurious it is. So we're going to be taking these sort of parameterizations for products. The monopolist is going to be selling to a space of consumers, and that's, again, it's going to be a subset of Rn. And the way we're going to parameterize these consumers is their coordinate corresponds to how much they like that parameter of the product. So in the car example of performance, efficiency, luxury, the corresponding coordinates of the consumer are how much they like those features. That means the dot product x dot y is the benefit consumer X obtains from a product Y. We're going to have a distribution of consumers. To keep things very simple today, it's going to be uniform on our domain. And the monopolist, before they sell the product, they have to acquire them. They're going to acquire them at cost C of Y. And again, to keep things very simple, I'm going to assume that that C of y is y squared on 2. So what is the monopolist's problem? Well, it's to maximize their profit. The profit they get from selling a single product y is the price they sell it for, which is going to be a function v of y, minus the price they paid, y squared on 2. But of course, the monopolist doesn't get to choose what product a given consumer buys. So in fact, the monopolist's product is the integral over the space of consumers of v of yu of x minus yu of x squared on 2, where yu of x is the product chosen by a consumer x. And this sort of adversarial nature of the problem, it's where convexity enters from, and it's what makes this problem so interesting to study. Because this product yu of x, chosen by a consumer, it's going to be the one that maximizes their utility, where utility is the benefit to them from the product minus the price they paid. i.e., consumer x is going to choose the product y, realizing the supremum of x dot y minus v of y. And as notation, I'm using yu of x for the y realizing the supremum. So I want to maximize that integral above, but I have to do it subject to the consumer getting to choose their product. Now, for anyone with a bit of a background in convex analysis, this u of x defined as sup x dot y minus v of y, it's a Legendre transform. It's going to be a convex function. That's where convexity is entering from. But let me give you a bit of a reminder and background on Legendre transforms. So starting with convex functions, of course, a function is convex if for points x, y in your domain, the line joining u of x and u of y lies above the graph of that function. And of course, this definition works fine in 1 dimension, in 2 dimensions, in n dimensions. But there's an equivalent way to define a convex function. We're going to take our convex function from above, and we're going to note that any point, I can hit it with a support plane. And if I do that at every point, I'm going to recover my function. So that gives us an equivalent way of defining a convex function. Basically, a function u is convex if it's a supremum of affine supports, i.e. if it's of the form sup x dot y minus v of y for a given function v. And that's looking like the expression we had on the previous page. Let me just remind you of a few more points. For almost every x in our domain, that supremum is obtained. It's attained at a y which satisfies y is equal to du of x. And then, of course, because that supremum is attained, we have the expression u of x is equal to x dot du of x minus v of du of x. So let's go back to our model derivation and see how this optimization over the space of convex function arises. So from 2 slides back, we've got our problem. It's maximized the integral of v of yu of x minus yu of x squared on 2 over the set of v, where our yu of x was the argmax of x dot y minus v of y. But now we recognize that max or sup of x dot y minus v of y is a Legendre transform, and that attainment, that yu of x, is going to occur at du of x. So I can rewrite my problem. It's maximized the integral of v of du of x minus du of x squared on 2 over my price menus v, where u is the Legendre transform of that function v. But of course, at our attainment point, we had an expression for v of du of x, so we can substitute that in. We want to maximize the integral of x dot du of x minus u of x minus du of x squared. But now that v is not appearing anywhere in that integrand, we may as well just maximize over convex functions u. And there's an additional constraint here, which I haven't spoke too much about. It's the positivity or non-negativity of u. And that just means sort of, as a rule, your monopolist can't price products so high that consumers are attaining negative utility. So we've obtained our maximization problem over the space of convex functions. And I'm going to complete a square and I'm going to switch it to a minimization because it's a bit more standard. But we've got our problem we want to look at. Minimize the integral of du minus x squared plus u over the space of non-negative convex functions. So before we start looking at some results for it, let me explain 2 things. First, the model has some significant consequences from the modeling perspective, which are not too hard to derive. And the second, the model has similarities to, and is going to present similar difficulties to, the obstacle problem. So what do I mean by significant consequences, and what do I mean by get them fairly easily? Here's a theorem due to Armstrong. Assume in the setting from the previous slides, our set of consumers X is strictly convex, and our products are in the positive quadrant, two very reasonable assumptions. Then the function U, which maximizes the monopolist's profit, prices out a positive measure set of consumers. In economic terms, if your monopolist has correctly maximized their profit, then a positive measure set of consumers can't afford to buy a product. It's a kind of depressing fact, but it actually follows without too much work from just the statement of the model. We're going to need one lemma. It's the differentiation formula for moving regions. I mean, it's pretty standard. You can find it, for example, in Evans's appendix, the textbook, the appendix to Evans's textbook. So of course, if we want to differentiate an integral where the function we're integrating depends on time, then I hope to be able to just differentiate onto the integral sign. And you can do that with some fairly standard conditions on f. If, however, our region also depends on time or a parameter, then we pick up a boundary term. So more precisely, if we've got an evolving family of domains, an integral over them, then the time derivative of that integral satisfies this expression on the right-hand side. It's what you'd get from differentiating under the integral and a boundary term. So this is the only tool we're going to need to prove this result called the desirability of exclusion. So I'm going to leave it up there. And I like to include this result because I think it's got a proof that if you sort of concentrate, you can understand, and it's quite a compelling result. So I'm going to take my minimizer to my previous problem. What tools do I have to work with? All I know is it's the minimizer. So if I put in some other admissible function into the functional I'm minimizing, I increase its value. So I am going to try putting in some other function. I'm going to take my U, my minimizer. I'm going to assume for a contradiction that the set on which it's zero, i.e. the set of consumers who can't afford to play, doesn't have positive measure. I'm going to take my function U. I'm going to drop it down by some small amount t, i.e. consider the function U minus t. Now, of course, that's not admissible because it could be negative. So I patch it up by taking a max of U minus t and 0. Now what I want to do is consider the value of the functional phi on this new competitor function, U of t. Well, let's plug it into the integral. I get a half dut squared plus ut minus x dot dut. This is just the integral we're working with. Now, what can I say? Well, I can say this integrand is non-zero only when u is greater than 0, only when ut is greater than 0, i.e. when u is greater than t. So my region of integration is the set where u is greater than t. And on that region, ut is equal to u minus a constant, so its gradient is unchanged, i.e. I have a half du squared minus x dot du, and ut is just u minus t. So I plug in that term. Now, I said all I have to work with is minimality, i.e. this expression phi of ut having a minimum at 0. That implies its derivative at 0 is non-negative. Now I can go ahead and compute the derivative of that thing using that formula from the top line. So what have I got? First of all, I pick up a boundary term. That's this second term. And I'm not really going to care what it is for now. I just note that it is a boundary term. And then I also pick up my term from differentiating under the integral sign. So when I look at that integrand, what has a t attached to it, i.e. what doesn't vanish when I differentiate, a half du squared vanishes, u vanishes, minus x dot du vanishes, and I'm left with minus 1 times the integral over the set u greater than t, which at time 0, an integral of minus 1 is just minus the volume. So I end up with this expression, this inequality. 0 is less than or equal to the volume of the set where u is greater than 0 plus a boundary term. Now, I said I don't care what the boundary term is, but what I do care is the set where u is greater than 0 is going to have positive volume. So there's a big negative term leading this inequality. The only way I can compensate and get something non-negative is if this second integral is positive. I can only have a positive integral if I'm integrating over a set of positive measure, i.e. the boundary of the set where u is greater than 0 within our domain X has positive measure. For convex domains, which this set is in higher dimensions, that's enough to imply this set has positive measure. So it's not quite a one-liner, but it's certainly a one-page proof that gives you this model has some very interesting economic consequences. Now, we want to talk about why this model is interesting mathematically. So model's up there at the top, and I'm going to remind you of two other very popular models in the calculus of variation. So the first, certainly what I consider the most well-known PDE or variational problem, minimizing the Dirichlet energy, which is going to give us Laplace's equation. So if I want to minimize the integral of du squared, subject to a boundary condition u equals f, I'm going to obtain a minimizer, which is a harmonic function, i.e. satisfies Laplacian u equals 0. This is a well-known fact. Minimizers of the Dirichlet energy are harmonic functions. That means they're C infinity, they're analytic. As far as regularity theory is concerned, they're as well behaved as we could possibly hope. But if I modify my minimization problem with one small change, I'm going to obtain something far more poorly behaved. So I'm talking about the obstacle problem. The obstacle problem is as follows. Minimize the integral of du squared, the exact same integrand, subject to u equals f on the boundary, the exact same boundary condition, with one additional condition. U is greater than or equal to some other function g. I.e. my function u, it lies above an obstacle, and that obstacle is g. Now, solutions of the obstacle problem, they're not even C2. And the boundary of the set where your function hits the obstacle can have a very complicated structure, i.e. this seemingly innocuous change to the problem of just requiring u be bounded below by another function destroys the regularity theory. And let me explain why that is. So we started with minimizing the Dirichlet energy, i.e. taking some boundary data and finding the harmonic function with that boundary data. When we switch to the obstacle problem, what am I doing? I'm taking my harmonic function, I'm jamming an obstacle up underneath it, and I'm requiring my minimizer lie above it. So I'm going to obtain something that is equal to the obstacle on some subset of my domain and harmonic elsewhere. Now, where it's equal to the obstacle, it necessarily has the same Laplacian as the obstacle. So in, for example, this example, where my obstacle is a paraboloid and has Laplacian equal minus 2n, our minimizer, it's harmonic where it doesn't touch the obstacle, so it has Laplacian equals 0. But where it does touch the obstacle, it has Laplacian 2n. So our Laplacian, and thus at least one of our second derivatives, is discontinuous, and our function is not C2. And I want to stress that our Laplacian of our minimizer, it's got a jump discontinuity, and here, for example, it's 2n times the characteristic function of the set where b is greater than 0. These sorts of obstacle problems where we've got a Laplacian with a jump discontinuity and equal to a characteristic function of the set where something's non-negative are going to show up again and again in this talk. And let's just understand what this means for our model. Well, we wanted to minimize the integral of du minus x squared on 2 plus u over non-negative convex functions. So if I was just doing the minimizer of du minus x squared plus u with some suitable boundary conditions, that would be a fairly good problem. My Euler-Lagrange equation would be Laplacian u equals n plus 1. And again, I'd have C infinity smooth solutions. If I don't include my convexity constraint, but I do include a non-negativity constraint, i.e. if I want to minimize the integral of du minus x squared on 2 plus u over non-negative functions, then I'm going to get a classical obstacle problem, like what we just looked at. In fact, I'm going to get Laplacian u is equal to n plus 1 times the characteristic function of the set u greater than 0 with a boundary condition. But we want to do something even more complicated. We want to minimize this thing with a convexity constraint. And now we're not going to obtain just two regions of different behavior, i.e. equal to the obstacle and greater than the obstacle. We're going to obtain at least three regions, a set where you're positive and strictly convex, a set where you're convex but not strictly convex, and a set where you're zero, where that constraint binds. And a big part of the talk is going to be discussing the behavior of these sets. Before we do that, let me give you a bit of history. So this problem was first studied by economists, and indeed all the works from 78 through to 98 are primarily the works of mathematical economists. Then this was picked up by the mathematics community, in particular Cale and Lagrangian. They proved C1 up to the boundary regularity, which is something we're going to need. Basically, your minimizer U has a derivative up to the boundary. This was improved by Caffarelli and Lyons, who improved this to C11 lock. And more recently, prior to my work with them, Robert and Kelvin had some work on new Euler-Lagrange equations. And you can generalize what we've done here in a bunch of different ways by replacing where we had an x dot y with something more complicated. And again, there's some very important works by Fagala, Kim, and McCann, and Shibing Chen in this regard. But our focus today is on this problem with b of xy equal to x dot y. And the first thing we want to talk about is the free boundary structure of this problem and the derivation of some new Euler-Lagrange equations, which kind of reveal a hidden obstacle problem that was there in this problem all along. So we want to talk about free boundary regularity, i.e. we have these regions where the function behaves essentially radically different in each of these regions, and we want to understand whether the boundary between them is smooth. This is a problem in the broader field of free boundaries. So for the obstacle problem, the regions were u greater than the obstacle and u equal to the obstacle. For us, it's going to be regions where the function is strictly convex and regions where the function is convex but not strictly convex, and also the region where the function is zero. So how precisely are we going to define these things? Well, what do we start with? We start with our minimizer, which we know is a C1 convex function. For C1 convex functions, at each point in the domain, our function has a support hyperplane. Now, that support hyperplane, it hits the function at least at the point where it's supporting it, but it may hit it on a larger set. It may hit it on, for example, a line segment or a set with open interior. Open non-empty interior. Now, what we're going to do is we're going to introduce some notation. For any x naught in the domain, p sub x naught is the support at that point, and x naught tilde is the set on which that support contacts u. Now, we're going to divide up our domain according to the dimension of these. So curly xi is the set of x such that x naught tilde has dimension n minus I. And I mean, you can kind of not think too hard about the definitions and just look at the pictures. So here's some convex functions that might be the one we're dealing with. Each of these functions, I've taken a point and I've taken its support plane at that point. And we can see if there's a region where our convex function is convex but flat, then that's going to be a point in x naught in 2 dimensions, i.e. where the contact set has dimension 2. We could take a support plane that hits along a line segment. That, again, in 2 dimensions would be a point in x1, or our point in, if you're a point of strict convexity, then that's a point in x2, or more generally, xn. So the first result I'm going to talk about today is the classification of these sets and the relation to an obstacle problem. And the result is as follows. Take your minimizer, then we can say a few things about these sets. First of all, x naught, which a priori was defined as the set on which u is affine, is in fact just the set on which u is 0, i.e. there's no portions like in this first picture where you're flat, except for the one where you're equal to 0. Second, in the region of strict convexity, we're basically back in the classical regime. The Laplacian of u is equal to n plus 1, and we've got a smooth function there. And moreover, the set on which you're strictly convex is open. Now, the next result is that for these other regions, so for example, in the picture, this line segment along which you're affine, all of these intersect the boundary. And what you're going to see in the talk is that that provides us with a very powerful tool for studying this problem. It's going to let us prove point 4, which is that in 2 dimensions, along the x1, x2 free boundary, u in fact solves the classical obstacle problem. And once we have a classical obstacle problem, we can obtain some regularity. Namely, we can say that wherever this free boundary is the graph of a Lipschitz function, it's in fact the graph of a C infinity function. So I want to talk a bit about the proofs of these results without going into too much detail. So the only thing we've got to work with is minimality. And as is standard for variational problems, we're going to take the fact that you're a minimizer and use it to define some variational inequalities. And they're as follows. If I have my minimizer u and any other admissible function u tilde, then I get the following inequalities just by doing essentially what we did in Armstrong's proof earlier. I put u tilde into the functional and I differentiate. That gives me an inequality for that derivative. And I can also integrate those things by parts to get the latter expressions. And I'm going to remark that I've got 2 families of inequalities here. One where essentially the quantity of interest, i.e. this Laplacian u term, is evaluated at u, and one where it's evaluated at our competitor function. And this is, again, something that turned out to be a very powerful technique because we can, for example, cook up competitors that are paraboloids and thus might have Laplacian n plus 1, in which case this inequality on the last line becomes very useful. So let me say a bit about how we'd prove this result describing x naught. Remember, that was the result that said if u was affine on a set of positive measure, then it has to be 0 there. The proof, it's 2 things. It's construct an admissible u tilde and plug it into the perturbation formula. So take my u, and suppose for a contradiction, it's affine, it's flat on a set of positive measure, but is not 0 there. I'm going to define a u tilde, a competitor function, by taking my u and dropping it down on the set, which is affine. Now, the function we've got there is not convex, but as a technical aside, you can patch it up so it is convex. Now, what's that function going to look like? Well, on that contact set x naught tilde, we have u tilde minus u is less than minus h, where h is the height we dropped it down. And again, on this contact set, they have equal gradients because all I've done is shift down. Now, when I put that into this perturbation formula, the third to last line, what do I get? I get 0 is less than or equal to u tilde minus u, which is minus h. And then I've got this in a product where du tilde minus du is 0. So that term vanishes. I've got 0 is less than or equal to minus h. That's a contradiction. And all you need to do to make this rigorous is justify that this part where you've patched up, it doesn't affect these estimates too dramatically. But these are the ideas behind the proofs. Because all we have to work with is minimality, we're constructing competitor functions and obtaining contradictions. Next, I want to describe Xn. This is the region where you're strictly convex. And what we're going to do is perturbation arguments. They're not too different from the ones before, but a key point is that we can prove the Laplacian of our function is equal to n plus 1 at any point in a section. And I'll remind you what a section of a convex function is. Here's a convex function. It's got an affine support at each point. I can take that affine support and I can shift it up. That set where u is less than the shifted up affine support is what we call a section of a convex function. We can do perturbations by paraboloids at any points in a section to obtain that the Laplacian u is equal to n plus 1 almost anywhere in a section that's strictly contained in the domain. And of course, points of strict convexity are, of course, contained in sections strictly contained in the domain. So we obtain, first of all, Laplacian u is equal to n plus 1 there. and that our function is C infinity by standard regularity results. So that's actually the W2n regularity theory, but we have W2 infinity by that C11 lock result I mentioned earlier. Now, by far, to me, the most interesting part of this classification is the fact that my contact sets upon which I'm affine always extend to the boundary. And this has quite, I think, a nice proof. It's by contradiction. We're going to take a contact set and we're going to assume that that contact set doesn't extend to the boundary. If it doesn't extend to the boundary, I can lift up my support, some small h, and obtain a section that is strictly contained in my domain and on which my function is affine on at least a line segment. So I've got a section, which means my previous result implies the Laplacian of u is equal to n plus 1. If I differentiate that equation twice, I've got that my second derivatives are harmonic functions. But by convexity, they're non-negative harmonic functions. So strong max says they're either strictly positive or zero everywhere. Because our section doesn't extend to the boundary, our function lifts up in all directions. Its second derivatives are not zero. So then they're strictly positive, which means you can't be affine along a line segment. So that gives us that classification, the first three parts of that theorem. Now we're going to talk about how we prove this connection to the classical obstacle problem. And we're switching to 2 dimensions now, because this is sort of the only setting in which we can prove these results. But we're going to consider the minimizer on a convex domain in R2. And we want to understand the free boundary between this set where you're affine along line segments and this set where you're strictly convex. Now, what we've just said is that those line segments along which you're strictly convex, along which you're affine, extend to the boundary. So I'm going to be able to use these line segments and their intersection point with the boundary as new coordinates for this problem. And it turns out in these new coordinates, you can obtain Euler-Lagrange equations, which previously we didn't know in this region. So let me give you the picture. I'm going to have a domain, and this sort of arc on the left-hand side is the boundary of my domain. I've got my 2 regions, x2, the region of strict convexity, and x1, the region along which you're affine on line segments. Now, each of those line segments, it has a direction z of t and a point where it hits the boundary, gamma of t, by our previous result. We're going to take as coordinates r and t, where t is the coordinate of a curve parametrizing the boundary, and r is your length along the line segment which hits the boundary. And so I've said that a bit more precisely on the previous slide. For a connected portion of x1, the set where you're affine, and a smooth portion of the boundary, parametrized by a curve gamma of t, we're going to choose coordinates r of t, satisfying x of rt is equal to gamma of t plus rz of t, where z is the direction of that point and r is your distance along it. The maximum distance you can move along it before hitting x2 is capital R of t, and that function capital R of t defines our free boundary. So studying capital R of t is what we want to do to study the free boundary. So I've claimed you get some very interesting Euler-Lagrange equations in these coordinates. And I won't give a full derivation of them, but I'll give the basic idea. I've started by saying that what we want to do is study this function capital of R of t. And then I've rewritten our variational inequality from an earlier slide. Something that was actually present in Roche and Chonet's early work, but I think not super picked up on by the community, was that these variational inequalities hold not only over the whole domain, but restricted to individual contact sets. And that's very powerful because we can take this inequality and we can compute it in our new coordinates. And it's standard multivariable calculus, but what you get is below. Why this is so useful is because when you put it back into that variational inequality and make some good choices of your comparison functions v, you're going to get out 2 useful equalities. The first, equation 5, which I refer to, but probably not very correctly, as the Euler-Lagrange equation for the free boundary, because it describes this function r of t in terms of our minimizer u, is the following equation. R squared of t is equal to some quantities defining our parameterization times the boundary data, du minus x. And this second equation, which is, I call the Euler-Lagrange equation for the function, is 3 minus Laplacian u is equal to 3r minus 2r of t. This is a very useful and very easy to understand equation, because remember that in x2, the region where you're strictly convex, we have Laplacian u is equal to n plus 1, i.e. in 2 dimensions, Laplacian u is equal to 3. So this thing, it tells us how far off we are from satisfying Laplacian u equals 3, because we can see that, for example, at the endpoint where little r is equal to capital R, we have 3 minus Laplacian u is non-negative, well, positive, so that Laplacian u is strictly greater than 3. That's a jump discontinuity, i.e. we're back in obstacle problem realm. So this Euler-Lagrange equation tells us that we have an obstacle problem at the free boundary. It tells us that the Laplacian looks like some function plus a jump discontinuity across x2. So we want to start being able to apply regularity results for the obstacle problem. We need to work out what the obstacle is. What it turns out to be is that our function u solves an obstacle problem where the obstacle is the minimal convex extension of u restricted to x1. Let me remind you the definition of the minimal convex extension. Take u on x1, i.e. the region upon which it's affine, take those affine supports and consider the supremum of them. That function there is the minimal convex extension. And again, I've got some pictures. So here's a convex function, which has a region, the bowl part, where it's strictly convex, and has a region where it's convex but not strictly convex, the half-pipe region. I can take the affine supports on the non-strictly convex region, and I'm going to get this minimal convex extension. I can look at the difference between my function and the minimal convex extension, and it's going to be 0 wherever these things were equal and positive elsewhere. And that thing is going to solve an obstacle problem. And this is what this slide is saying. Our minimizer u solves an obstacle problem where the obstacle is the minimal convex extension on x1. So this sounds great. We've got an obstacle problem. Can we just apply the classical regularity theory for the obstacle problem? The answer is a priori no. The classical regularity says the free boundary has one more derivative than the Laplacian of the obstacle. But because our obstacle is a priori C11, i.e. its Laplacian is merely a measurable function, we can't apply the classical regularity, and that's okay because we expect singularities at the free boundary. So something would be wrong if we could just apply the classical regularity. But we can say that if our free boundary is Lipschitz, then the classical regularity theory for the obstacle allows us to bootstrap to that to C infinity. And I think in the interest of time, I'll skip over that bootstrapping. But it's just that these two equations from earlier, 7 and 8, well, 7 says that R essentially has one more derivative than U, and 8 says that R has, sorry, 7 says that if R is Lipschitz, du is Lipschitz, and then 8 tells us that R has two more derivatives than U. So these things are gonna, this is sort of a standard bootstrap now, where we get U has an additional derivative over R, and then R has an additional derivative over U, and we can repeat this up to R being C infinity. So in this second half of the talk, I want to talk about, we've got some basic regularity for families of domains now. We want to look at what the minimizers look like in a special case. And the most well-known but not entirely understood case was squares in the plane, i.e. a domain X, which is the product of a plus 1 for some value a greater than 0. And I mean, this problem has been pretty well studied for a long time, and lots of people have put effort into coming up with numeric or analytic descriptions, but these weren't entirely complete yet. So going back to Roche and Chaunet, who were the first person to study this, they obtained some key properties of the solution. They basically inferred that it would look as follows. You'd have a triangle where your function is equal to 0, in their notation omega naught. You'd have a large region where the function is strictly convex, in their notation omega 1, taking up most of your domain. And then you have a region where bunching occurs. So that's where your function is affine along line segments. And this, they sort of had a description of, but we can give a more precise description of now. They inferred that all the line segments along which you're affine would be orthogonal to the diagonal. And that implies this second picture. This second picture is a picture of the image of the gradient. Remember that a consumer got to choose their product, and it was this mapping we called yu of x, which turned out to be the gradient du of x. So the image du applied to the domain gives you the set of products sold. And originally it was believed that it sort of looked like this. It was a square containing your domain and a line segment back to the diagonal. And sort of our more refined approach now lets us give some more accurate versions of this. So in fact, it was some numerics due to Mirabeau and also some earlier authors, which sort of suggested there might be a bit more to it, to this solution. So I'm taking some numerics from Mirabeau's paper, which implies, first of all, that this configuration of domains, omega naught, omega 1, omega 2, will look similar, but not quite like what Roche and Chaunet conjectured. And again, this distribution of products sold will not quite just be a square and a line segment, but something a little smoother. So the numerics indicated there was a bit more to do here. Now, McCann and Zhang, Robert and Kelvin, they determined conditions for these solutions, which the numerics were hinting at, to be the correct solution. So they conjectured that it would look like this, a region where you're 0, a region where you're affine along line segments orthogonal to the diagonal, and 2 additional regions, which were showing up in Mirabeau's numerics. And they gave conditions for the solution to be of this form. And part of my recent work with Robert and Kelvin is to show that those conditions are satisfied, provided A is sufficiently large. But there's that caveat, A is sufficiently large, because not only did we prove that this is the solution for A sufficiently large, we found some new behavior for A small and A equal to 0. So that's what the focus of this second half of the talk is, describing the solution on these squares A plus 1 for all possible values of A. And I mean, here are the pictures. For A equals 0, you've got only an omega naught and omega 2 region, no omega 1 region. For A sufficiently small, you've got an omega naught region, an omega 2 region, and these 2 omega 1 wings, essentially. Then for A sufficiently large, you've got the behavior of the solution that was showing up in those earlier numerics. Omega 2, omega naught, 2 wings, omega 1 minus, omega 1 plus, and a region where you're affine along line segments crossing the domain. So this is our second theorem. Take your minimizer U, then we can say the following things about it. First of all, X naught, it's always a non-empty convex set situated in the lower left corner. Second, when A is sufficiently large, we've got a very crude estimate of 7 on 2, whereas, so I think 3.5-ish, but really it should be a half-ish. Then there's a non-empty portion of X1 consisting of rays orthogonal to the diagonal. So that's this quadrilateral omega 0, 1 in the third picture. Our third point, there are always 2 disjoint components of X1 in which rays have only one endpoint on the boundary, satisfying those Euler-Lagrange equations we derived before. Our fourth point, this region X2 is non-empty and contains the east and north boundaries. And finally, we've got some regularity up to the boundary, which we needed to prove. So this is a very explicit description, and I want to say a bit about why we could obtain such an explicit description. Well, it's because we're in 2 dimensions, and not only are we in 2 dimensions, but because these rays we were dealing with before hit the boundary, we can turn this into a 1-dimensional problem and only consider its behavior along the boundary. So to do that, we're going to need a lemma, which is that points on the boundary are points of strict convexity if and only if our boundary condition, here it's the Neumann condition, du of x0 minus x0 dot n is equal to 0, is satisfied. Why this is so useful is because it means we'll be able to study our problem by considering the behavior of this 1-dimensional quantity. If it's 0, you're in a point of x2. If it's non-zero, you're in a point of x1. So we're going to go back to our earlier Euler-Lagrange equations. Our parameterization simplifies a bit because our boundary curve gamma is now a straight line, AH of theta, and our directions we're going to take as cos theta, sine theta, where theta is the angle they make with the horizontal. Our Euler-Lagrange equation we wrote down earlier, it's even simpler in these coordinates. It's r squared of theta is equal to h dash of theta dot du minus x dot n. And note, we've already got some monotonicity occurring here. Our line segments have to increase in angle as they go up the left-hand side. So the basic idea behind the proof, as I said, we're going to consider the behavior of this function along a boundary curve. So moving up, we're going to take, for example, the west side, i.e. a times the interval a plus 1. So we can adapt that proof we started with, the necessity of exclusion, which you may recall required a strictly convex domain, but we've got enough symmetry to make the same result work here. Some fairly direct variational arguments of the form we started with, i.e. cooking up competitor functions, give us the convexity along the north and east boundary. Now, we want to consider the configuration of these x1 regions. Because the top part of the domain, what I'm calling the north side, is contained in the strictly convex region, there the boundary condition is satisfied, i.e. du minus x dot n is equal to 0. On the other hand, we've got this region where our function is equal to 0, and there the boundary condition cannot be satisfied, because if our function is 0, du minus x dot n is equal to a. We've got our C1 regularity, which means this jump between du minus x dot n equals 0 and du minus x dot n equals a cannot be a discontinuous jump. Something has to happen between x0 and x2, and that's an x1 region. Our Euler-Lagrange equations in this x1 region consisting of rays which have only one endpoint on the boundary is such that you get a C2 estimate. And that C2 estimate is independent of A, which means for A sufficiently large, that C2 estimate can't everywhere hold if du minus x dot n is moving between 0 and A. So our Euler-Lagrange equations can't always hold. And the only alternative to the Euler-Lagrange equations is rays with both endpoints on the boundary. So that tells us for A sufficiently large, not only are there our Euler-Lagrange equation regions, but there's a region where rays have both endpoints on the boundary. So there was a final part of this theorem, which was that this x01 region was vanishing for A sufficiently small. And I think this was something not previously seen before, but it has a relatively pleasant proof. We're going to consider this problem, which was on the square with lower vertex AA. And we're going to assume for a contradiction that this x01 region of rays crossing the diagonal orthogonally exists for all A sufficiently small. Then we can take the limit. Well, first of all, we can reflect this problem into each quadrant, and we can take the limit as A gets sufficiently small. In the limit, we're going to recover the solution for A equals 0. Now, under our conjecture that the solution looked like this for all A sufficiently small, we're going to obtain a limiting solution, which still looks like this. Note, however, that we said rays must intersect the boundary, and they can't intersect the north or east boundary. By reflection, that means rays for the A=0 problem can't intersect anywhere on the boundary. Because rays must intersect the boundary, that implies rays don't exist. So we only have an omega-0 and an omega-2 region, i.e. under our hypothesized form for a contradiction, the solution for A=0 looks like this, i.e. it has a diamond where U is 0, and it has a region where the Laplacian U is equal to 3. But of course, a function of this form is a solution of the classical obstacle problem. Laplacian U is equal to 3 times the characteristic function of the set where U greater than 0. And Caffarelli's free boundary regularity results for the classical obstacle problem imply the set where U is equal to 0 in this setting has smooth boundary, so it can't be of this form. And this is our contradiction that implies our omega-1,0 must vanish, and essentially completes me showing you the key ideas of this proof. And so that proves our description of these regions. But as I said, two things actually hadn't been observed before. One was the vanishing of this omega-0,1 region for A sufficiently small, and the second was this vanishing of omega-1 entirely for A=0. So we proved this analytically, but we subsequently went back and generated some new numerics, and I thought it would be nice to show those. And you can see that, yes, it does behave exactly as the theory suggested, because here are the pictures of the new numerics. For A=0.6, we've got a winged region and a region of rays crossing the diagonal. For A=0.4, we now just have 2 winged regions, no rays crossing the diagonal. And as that A shrinks down, those winged regions shrink to 0. The set where U is equal to 0 becomes, up to the poor resolution of these numerics, something smooth, not a diamond. And I spoke a bit about the distribution of products sold, which, I haven't talked about as much as I'd like, but is quite an interesting part of the problem from the economics point of view. Now, this was the set that was originally conjectured to be a square with a line sticking out of it. But again, you can see the numerics for this set once again line up with what the new theory says. For A sufficiently large, you've got a line on the diagonal, just as was initially conjectured. And then we've got these thick lines, which correspond to the 2 wings, and then everything else is the strictly convex set. And you can see that, again, for A sufficiently small, that diagonal line, i.e. rays crossing the diagonal, vanishes completely, but you still have these thick boundary lines, and then that too disappears for A=0. So this sort of is just a recent check or a recent generation of some pictures that confirm the results in that theorem, which we're pleased to see. So let me finish with some outline of future work. So I'd like to describe the singular set a bit more precisely than what we did on the square. I would like to consider this problem in n dimensions. I'd like to consider removing those simplifying assumptions we started with, which were that our function is, at the start of the talk, I made 2 dramatic simplifying assumptions, that our consumers have a uniform distribution and that our cost to the monopolist was y² on 2. It would be good to remove those. And I mean, it would be good to deal with some related models. So, for example, a very well-known problem called Newton's problem of minimal resistance, it's to minimize the integral of 1 on 1 plus du² over convex functions bounded below. So this is actually a problem that's been known for much longer, but hopefully it will sort of yield to the same tools because it's essentially of the same form, minimizing an integral over the space of convex functions. That's everything I wanted to talk about. So I'll leave it there. Thank you, everyone, for listening.
Thanks for giving us your talk, Cale. Does anyone have any comments or questions for Cale?
Yeah, I'll come in if nobody else does at the moment. Yeah, I'm just wondering, so you were able to prove these later results in 2 dimensions, but do you know, or do you have any, I guess, intuition or idea of what you expect to happen in general, like in higher dimensions? I mean, is there any reason to expect, I don't know, anything to go catastrophically wrong, or do you think it should just generalize as expected?
Well, I think when you're moving from 2 dimensions to 3 dimensions, it's more typical to expect everything will go catastrophically wrong. There is a lot of results that hold for 2 dimensions and not higher. So I mean, the main difficulty is that we had two easy to describe regions in 2 dimensions, the set where you're affine along line segments and the set where you're strictly convex. Once you move to 3D or higher D, there's more regions to deal with. So in 3D, it's the set where you're strictly convex, the set where you're affine along planes, and the set where you're affine along line segments.
Okay. Right.
So you got more free boundaries to deal with, and it is, for example, unclear as to whether each of these sets will be non-empty. So I don't know if I can draw a cube, but I'll try. I mean, so you can, for example, consider the distribution of products sold. So remember, for us, it looked like a square with a stingray's tail coming off it, essentially, in 2D. In 3D, some early numerics suggest it looks like a cube with a stingray's tail coming off it, and each of this tail has 2-dimensional fins. So 3 fins. So they look like things that are not of full dimension. So studying the function on those thin sets is going to be quite difficult.
Right. Okay. Okay. Interesting. Cool. Thanks.
I have a question. You're dealing mostly with the square here.
Yes.
If instead of going in higher dimensions, you stick to dimension 2, are there situations where other polygons would show up, for instance?
Yeah, I mean, squares are symmetric. As
So
soon as you
you want
become,
that symmetry.
so things become easier. It would be reasonable to study this on convex domains in 2 dimensions and see what you can prove. And you can prove some free boundary regularity results, but to my knowledge, no one has actually looked at the configuration of these domains in as much detail as on the square.
So what's the symmetry group that you're relying on there? Is it just Z2 cross Z2, or is it something else?
We're just relying that on a square, the solution looks the same on both sides when you cross the diagonal. So that, for
Okay, so
example,
it's just a Z2 symmetry then.
mhm.
I mean, like the triangle has a Z2 symmetry. Would
Yeah,
I'm just being silly now, but
no,
yeah.
there's nothing a priori
So
silly about
I'm just
asking.
yeah, I was just trying to work out what's so special about the square compared to other 2D shapes, and it sounds like it's just symmetry along the diagonal.
Well, if you're asking that because it's the one we studied, it's more that it's become kind of
The standard thing to do.
the prototypical example to study. So
Okay.
it was, for example, the popular one with numerics because lots of people had done it, so it's easy to compare your numerics to the existing ones.
Yeah, sure. That's fair enough.
But there's nothing from the application's point of view that says a square is particularly reasonable.
Yeah, cool. Any further comments or questions for Cale? In that case, let's thank Cale again for taking us through the Monopolists problem. Thanks all.